Okay, guys, welcome to Physics 203 Class 7. This is on the photoelectric effect, which is another of the experiments that are leading us to understand the need for new physics, quantum physics, to supplement the classical physics which you've learned in your first couple semesters at Roanoke, first few semesters at Roanoke. And the photoelectric effect was discovered around the same time as blackbody radiation, which we just studied, but is, of course, a different effect and maybe a little bit mathematically clearer or conceptually clearer why it requires a particle or photon theory of light. So, the apparatus for the photoelectric effect is shown here. We have a vacuum tube, and inside there's an emitter, which is usually made of some kind of metal, and we shine light, or just light, that is electromagnetic radiation, on that emitter. And if conditions are right, we can get that can free electrons from the emitter. So we shine light on an emitter in an evacuated tube. And under the right conditions, we can get an electron photocurrent, so electrons traveling across this vacuum tube, which will then continue through the circuit and register on this ammeter. And often in the experiments, or always in the experiments, there's also a power supply here, which we can adjust the power supply to apply a back voltage which can stop a given photocurrent. So, so if we have a photocurrent flowing of a certain magnitude, that there must be some positive voltage causing it to flow. And if we apply a back voltage, that will stop the photocurrent from flowing. And we use that back voltage to measure the maximum energy of the voltage here that causes the current to flow, and therefore the maximum kinetic energy of electrons going across this tube. So, okay, before we get into the what was observed for the photoelectric effect in the 1880s and 1890s, I'm going to define something for you and give you a little bit of the theory of metals. So this is a metal like the emitter in the photoelectric effect, and this is the light coming in and potentially emitted electrons if the conditions are right. And it turns out that our modern theory, we understand that electrons are bound or energetically bound inside of the metal by different amounts. So some electrons take a little bit of energy to get out of the metal. Other electrons take more energy to get out of the metal. And that's measured by a binding energy, E sub B for E binding, which would apply to each and every electron. So this would be highly bound, this would be less bound, this would be less bound, and so forth. And the so-called work function, and the name work function was just used. It's not a great name. It was used initially in studies of metals, and it's just stuck. I guess it's just what you need to get the current to work, so you call it the work function, is the smallest of the binding energies. So in this picture, it would correspond to this electron here. So the work function phi is the binding energy, EB, of the most weakly bound electron, the electron that would be easiest to input energy to and get out emitted from the metal. Okay, so that's the definition of the work function phi, the binding energy, the most weakly bound electron. And this is just a table taken from our textbook of different work functions. These are in electron volts, which an electron volt is around 10 to the minus 19 joules. It's actually 1.6 times 10 to the minus 19 joules, so it's a small amount, but we're dealing with atoms here, so that's not surprising. We have small energies. You can see they range for different metals: silver, aluminum, carbon, cesium, copper, anywhere from just under 2 to just over 5 electron volts. So a range of maybe 3 electron volts in for the work function. Okay, so experimental results on the photoelectric effect. It was first noticed by Hertz. You may know Hertz as the unit of frequency, and he did experiments on Maxwell's electromagnetic waves, but at the same time he noticed, as he was producing those waves, this photoelectric effect. And so he did some very initial work on it, but the main work on it was done by a guy named Philipp Lenard in the 1890s, a German physicist, and also a couple others but Philipp Lenard was the principal one. So what are the main results here that were found by Lenard and a couple others? The first is that the maximum kinetic energy of electrons coming off of the emitter is independent of the light intensity. Okay, so if we take red light, let's say, and we're getting a current going through here, if we crank up the intensity, we don't get the maximum kinetic energy of these electrons as measured by how much voltage we have to put on to stop those electrons. Okay, so that's the back voltage is that the back voltage we need to stop the current is equal to the maximum kinetic energy of the electrons going across. That's independent of the light intensity. Okay. 2, the maximum kinetic energy of electrons depends only on light frequency for a given material. Okay, so if we have a given material, let's say copper or something, the maximum kinetic energy which we have depends only on the frequency of the light we use, say red light. It doesn't depend, again, on the light intensity. Third, a smaller work function. Remember, work function is the binding energy of the most weakly bound electron, means a smaller frequency is required for the photocurrent. And below a cutoff frequency, there's no photocurrent, regardless of intensity. Oh, I have some images to show that back up some of these. Excuse me. So here, for the first one, the maximum kinetic energy is independent of light intensity. We can see here for a given frequency, for intensity 0, 2, and 3 times some multiple, we find that the photocurrent goes to 0 at the same back voltage, which indicates that the maximum kinetic energy, which is related to that back voltage, is the same regardless of intensity. And then for the second one, apologize for backtracking here, but for constant light intensity, as we for a given material, as we change the light frequency, so as we increase the light frequency from F3, which is the smallest, F2 to F1, it takes more, the maximum kinetic energy of the electrons is greater and greater because this back voltage gets greater and greater. All right. So a smaller work function means a smaller frequency is required for the photocurrent. And we can see that here. So here we have 3 metals, silver, lithium, and cesium. And it turns out that if we plot the back voltage versus the frequency of light applied, the y-intercept, we'll see an equation which supports this later. The y-intercept is related to the work function. So a smaller work function, like cesium, means that we need a smaller frequency for a photocurrent to start. So the photocurrent starts for cesium right here, and cesium has the smallest work function. And the next largest work function here is for lithium, and lithium we need a little bit more, a little bit higher frequency to start to see a photocurrent. And then so on for silver, we need the largest frequency of all. And below a cutoff frequency, there's no photocurrent regardless of the intensity. So we can see that that's indicated by these dashed lines. If we go below a certain frequency for silver, we don't get any current. That's indicated by these dashed lines. We have essentially a negative back voltage, which indicates we don't need to stop the electrons at all. There are no electrons coming at all. And then if a photocurrent is produced, then its magnitude is proportional to the light intensity. So if we're in this region where a photocurrent is being produced, then the intensity matters. So the higher the intensity of the light, the higher the photocurrent will be. But again, below that critical cutoff frequency here in the dashed region, there's no photocurrent regardless of intensity. So the intensity only matters once we get past a certain cutoff frequency. And then fifth, it turns out that the photocurrent starts very quickly, regardless of light intensity. So even with a very dim light, if we a very, very unintense light, if we shine it on this emitter and we're going to get a current, the current pops on instantly. There's no real delay. Okay, so those are the main experimental effects that were discovered by Hertz and Lenard. And let's see how classical theory would be applied to try to understand the photoelectric effect. So classically, how does light interact with electrons, the electrons which are being liberated? Well, we know that classically Maxwell told us that light is made up of electric and magnetic fields, which are shown here. The red is the electric and the blue is the magnetic field. Here's the electron. So light would come along, these electric fields would exert forces on the electron, and gradually the electron would be oscillated to greater and greater amplitudes, okay, to given more and more energy by this continually passing electric field. So it would be pumped with more and more energy. All right. So let's look at our facts, experimental facts provided to us, and think about how the classical theory, whether it jibes with those facts. The maximum kinetic energy of electrons is independent of light intensity. Well, that wouldn't seem to make sense, because the more intense the light, the greater the electric field is. That's what light intensity is classically, is this electric field. And so that would mean that the electron would be pumped with more and more, greater and greater force, greater and greater electric field. So it would experience more and more shaking, and so we would expect to get more kinetic energy coming out for the electrons as the light intensity, as the amplitude of the electric field is increased. So classical physics doesn't do too well on that one. Second, the max kinetic energy of electrons depends only on the light frequency for a given material. Well, the frequency here, and you might remember that the frequency of light is related to the wavelength. The greater the wavelength, the lower the frequency, and vice versa. So it turns out that the amount of energy that's transmitted to this electron is not dependent on the wavelength. Okay, so it doesn't matter if the electric field comes along varying really slowly across a great distance or very quickly across a small distance. You still get the same net energy input to the electron. So that would mean that the maximum kinetic energy, the fact that it depends on the light frequency in experiment, and classically it's predicted that it wouldn't depend on the wavelength and therefore not on the frequency, is another check mark against applying classical theory to the photoelectric effect. Smaller work function means a smaller frequency is required for a photocurrent, and below a cutoff frequency there is no photocurrent regardless of intensity. Again, regardless of the frequency, so below a cutoff frequency or below a certain frequency would mean above a certain wavelength, there would be no photocurrent. There's no limit to how long the oscillations can be in the electric field, and they will still provide energy to the electron through the Coulomb force. So that one doesn't work classically either. One which does work is that if a photocurrent is produced, its magnitude is proportional to the light intensity. Okay, because if a photocurrent is being produced and classically the light intensity increases, that means we have a greater electric field, and we'd expect greater vibrations of the electrons here, and so more electrons coming off per unit time, so a greater photocurrent. So the classical theory does apply to that one. And last, the photocurrent starts very quickly regardless of light intensity. Well, that one doesn't do so well because for very low light intensity, that means very, very low magnitude electric field and magnetic field. So that would mean a very, very slow transfer of energy to the electron. So these electrons in the emitter would gather energy very, very slowly, and so it would take a long time for them to get enough energy to escape. So the photocurrent wouldn't start very quickly, regardless of the light intensity. So that doesn't work very well. Okay, so the classical theory doesn't do a great job applied to the photoelectric effect. What about a quantum theory? And it was Albert Einstein, at the same time as he proposed a quantum theory for Planck's black-body radiation formula in 1905, that he proposed an explanation for the photoelectric effect. So look something like this. Remember that Einstein said that light energy is transmitted or in the form of packets of energy or photons, and in this context, the photons would come in and enter the metal and interact with an electron, and then give off that transfer that photon energy HF to the electron. The electron would then need to be liberated from the material, but there might be some energy left over, okay, depending on the photon energy, and the leftover energy would show up as kinetic energy of the electron. E equals 1/2 mv squared is the kinetic energy. Okay, so by conservation of energy, the energy of the incoming photon would be equal to the energy it takes to get the electron out of the metal plus the remaining energy the electron has in the form of kinetic energy. And that's expressed here. HF, the photon energy, is the work function for the most weakly bound electron plus the kinetic energy of the electron as it comes out. Okay, so let's again take a look at our different experimental results from the photoelectric effect. The max kinetic energy of electrons is independent of light intensity. Okay, does that make sense in this theory? Well, in this theory, light intensity just would correspond, since light energy comes in packets. Light intensity would just mean there's more and more packets of which each have the same energy. So you have a lot of these photon packets coming in, but they interact on a one-to-one basis with these electrons in here. And so on a one-to-one basis, each packet is going to transfer only that energy HF. It doesn't matter how many there are, each individual one only transfers the same quantum of energy HF. So that means the maximum kinetic energy which we can get, which occurs when we're at the most weakly bound electron here, is independent of light intensity. Is independent of light intensity, the total number of photons. So that's a check for quantum theory. The maximum kinetic energy of electrons depends only on light frequency for a given material. That's clearly true. For a given material, phi, the work function, is set, as we showed in that table before. And so the maximum kinetic energy is proportional to the frequency. HF, the photon energy, would just increase linearly with the kinetic energy of the electrons, which are being liberated from the surface. So yes, a smaller work function means a smaller frequency is required for a photocurrent. Yeah, that's true. To get a photocurrent, we need at least some kinetic energy for the electrons coming off so that they can get across this gap. And so if the work function here is smaller, that means that for a given small kinetic energy, we would need a smaller frequency to provide enough energy to get the electron out, the work function, plus give it a little bit of kinetic energy. And then below a cutoff frequency, there's no photocurrent regardless of intensity. Yeah, that's true too. If the kinetic energy of an electron has to be positive, since it's 1/2 mv squared, so the smallest this can be is 0. And if this is 0, then we can solve for the frequency necessary to just barely to give 0 kinetic energy, essentially, which is the end of the photocurrent. And if we solve for that, so this is true, we get a cutoff frequency equal to just the work function phi divided by h. Okay, that's found by setting the kinetic energy equal to 0, which would be the first point at which there's no photocurrent. If photocurrent is produced, its magnitude is proportional to the light intensity. Does that line up with the quantum theory? Yes, it does. If photons are coming in and each of them or one of them has enough energy to liberate an electron, then if we increase the light intensity, there's lots more of them, we're going to get lots more electrons coming off. So that works as well. And then finally, the fact that was observed that the photocurrent starts very quickly, regardless of the light intensity, that is supported or consistent with the quantum theory, because again, this one-on-one interaction between photons and electrons. If a photon comes in, it's already got this packet of energy. It doesn't need any time for the energy to ramp up. So even if the light intensity is very small, even if there are very few of these photons coming in, they each have the required energy to liberate an electron. So the photocurrent might be very weak, but it would start up. It would start up right away because each individual, even though they're rare, each individual photon would be enough to liberate those electrons. So that's a check as well. So Einstein came up with a very persuasive theory to explain the photoelectric effect. As with any new theory, this controversial assumption that photons carried energy in discrete packets. Robert Millikan, who you remember from the oil drop experiment, finding the charge of the electron, actually did experiments trying to disprove Einstein's explanation here of between 1905, I think, and 1916. But in fact, his experiments wound up supporting it, and he was man enough to admit that. And and Einstein won his Nobel Prize in 1921 for his explanation of the photoelectric effect of this very explanation, not for relativity, which many people think so. So, in summary, the photoelectric effect was an interesting phenomenon noticed in the interaction between light and matter, and classically speaking, with electromagnetic waves interacting with electrons, it was the intensity of the light which mattered in transferring energy, but experimentally the light intensity was seen to be not a great factor. Many things were independent of light intensity. Whereas in the quantum picture proposed by Einstein, with the energy packets proportional to HF, where F is the frequency, we can get agreement with the experimental results and see some of these tricky things and see why the currents cut off, and why the maximum kinetic energy is independent of light intensity, and so forth. So this was another experiment in strong support of the quantum theory of light, of photons. Thanks for your attention, and I will see you in class.